On a modern industrial assembly line, throughput is everything. Thousands of components move past stations every hour, and a single mismatched part can halt production. Human visual constraints create a persistent bottleneck when attempting to rapidly distinguish between 25 highly similar mechanical classes, such as differentiating a standard hex bolt from a machine screw in a fraction of a second. The engineering goal is to automate this process using a high-accuracy computer vision system. To be practical, this system must achieve near-zero latency while running natively on standard mobile edge hardware. This requirement demands a model that can look at a crowded workbench and instantly identify overlapping components without remote server processing. This image demonstrates the active bounding boxes generated by our deployed edge model, successfully isolating a nut and 2 screws on a physical surface. It tracks these components in real time, locking on with a 76 and 84% confidence threshold. While these results prove that edge-deployed precision is achievable, reaching this stage requires overcoming a massive foundational data hurdle. This is the cold start problem. There are no comprehensive, publicly available datasets for these 25 specific industrial parts. Training a robust machine learning model requires tens of thousands of varied images. Relying on manual photography to capture every possible orientation and overlapping state is logistically and financially unviable. The entire system must be architected from scratch. This requires a strict engineering pipeline, synthesizing data, mathematically balancing features, and designing hardware-aware deployment logic. The first phase of this pipeline involves generating the required ground truth training data entirely through simulation. Because an AI model cannot function without a robust dataset, systems engineering begins strictly with synthetic data generation. This flowchart details the synthetic dataset creation pipeline used to bootstrap the training data. We import standard CAD models and mathematically render them under varying virtual lighting conditions to simulate physical objects in 3-dimensional space. By recording these renders and extracting the individual frames, we generate a baseline library of clean, perfectly isolated mechanical components. This image grid reveals the visual contrast between the domains. The pristine, gray 3D renders at the bottom lack the messy, cluttered context seen in the physical photographs at the top. Mixing perfectly clean synthetic renders with raw real-world images creates a severe domain gap, often leading to total model failure during field testing. The primary technical obstacle within this gap is background overfitting. When trained on synthetic renders, the neural network may ignore the geometric edges of the part and instead memorize the uniform gray backdrop as the primary indicator that a component is present. A model trained this way fails on a busy factory floor because it has learned to identify the virtual environment rather than the part itself. To prevent this, the data pipeline must actively sabotage the model's ability to rely on background context. We resolve this by using the Segment Anything model, or SAM, to surgically separate the object from its original synthetic domain. This interface displays the semi-automatic mask generation applied directly to the raw images to isolate the components. Notice how the yellow and purple segmentation outlines tightly hug the geometry of the nut and screws. This pixel-level precision captures their exact structural features. Once isolated by the mask, the mechanical part can be completely decoupled from its environment. The isolated component is then algorithmically pasted across a series of rapidly changing, completely non-industrial environments to test its robustness. This technique is called background replacement augmentation, and it generates thousands of new composite training images. This grid displays the result: the same component forced into living rooms, grocery aisles, and outdoor spaces. This variety prevents the network from building spurious associations between the part and its surroundings. The augmentation forces the YOLOv8 Nano model to rely strictly on the structural shape of the component, closing the domain gap. Before training begins, the data undergoes one final enhancement phase, mapped out in this flowchart section. Mass-generating augmented images introduces the risk of dataset imbalance, which can bias the model toward overrepresented classes while neglecting others. We visualize the raw dataset as a high-dimensional space filled with unorganized data points. Passing these through the Dino V2 vision transformer extracts deep features, causing chaotic points to snap into distinct color-coded clusters based on visual similarity. Finally, k-means clustering is applied.
The algorithm targets the densest areas, identifying and pruning the redundant, near-duplicate frames from the dataset. This balancing ensures that the YOLOv8 Nano model trains on a representative distribution across all 25 classes. Raw data volume is a liability if it remains unbalanced. Rigorous feature clustering transforms random images into a highly optimized training foundation. With the model trained, the final challenge is running that inference natively on restricted mobile hardware. Continuously forcing a mobile processor to run machine learning inference causes thermal throttling and significant latency, degrading the user experience. This logic diagram reveals the architectural solution, integrating a stability check using Unity's AR foundation. Look at the moving branch. If the device's sensors detect physical motion, the system actively skips the machine learning detection phase to save compute cycles. During a fast pan across a workbench, hardware sensors override the inference engine. By pausing the feed, it prevents generating inaccurate predictions on blurred frames. The inference engine instantly resumes the millisecond the camera stabilizes, ensuring a completely seamless process to the operator. Successful edge AI relies on a systems-level architecture that manages hardware resources, rather than simply relying on the size of the neural network. The final step is translating this optimized backend into an intuitive user experience. This interface presents the engineer with two primary deployment options. In general detection mode, the system manages the output tensor by capping visual labels at 5 simultaneous components, keeping the screen readable in dense environments. Alternatively, the engineer can use the specific detection menu to mandate that the system search for one exact part out of the trained classes. This output demonstrates the active filter. The system ignores surrounding noise and isolates only the target component under physical, real-world lighting conditions. A 96% confidence score confirms the target, validating the model's ability to translate synthetic training into real-world detection. Engineering a pipeline from synthetic generation to hardware-aware deployment provides a structured framework for overcoming data scarcity in specialized industrial vision tasks.